Okay, so let us start our discussion on this set of protocols which provide kind of control functionalities or additional management functionalities along with the IP protocol at the IP layer. So this set of protocols, so out of that ICMP, ARP, these protocols run as a kind of additional protocol or the service protocol along with the IP layer. And NAT is a specific type of service to support large number of IP networks within a kind of subnet. So we'll discuss about the idea of NAT first, network address translator, and then we'll go with the protocols ARP, which stands for Address Resolution Protocol, and then ICMP, which stands for Internet Control Messaging Protocol. Now, to start with, so in the we have already looked into the IPv4 block of IP addresses. So we have seen that we have mainly 3 classes of IP addresses: Class A, Class B, Class C. And from these classes of IP addresses, the addresses are assigned to the end host. And Class B addresses are specifically reserved for the multicast IP, whereas Class E is reserved for the future use, particularly for the research purpose or creating small private networks, something like that. Now, among these set of IP addresses which are available with Class A, Class B, and Class C, some set of IP addresses have been designated as the private IP addresses. Now, what are the private IP addresses and why we move towards that direction? So first of all, a major problem with the IPv4 is that the number of IP addresses are limited. Well, so if you look into the scale of IP addresses which are available in IPv4, so you can assign host addresses from Class A, Class B, or Class C. Now in Class A, we know that there is 8-bit of network address and 24-bit of host address. Now with that, I can have 2 to the power 24 minus 2, that many number of different IP addresses which are possible. In case of Class B, it is 16-bit network address and 16-bit host address. So you can have 2 to the power 16 minus 2, that many number of hosts which are possible. Similarly, for Class C IP addresses, I have 24-bit of network address and 8-bit of host address. So I can have 2 to the power 8 minus 2, that many number of hosts available for every network. Now, if you just try to calculate the number of IP addresses that we have, that is very limited, and out of that we are also discarding some of the IP addresses for broadcast IP or the subnet IP, and whenever we are going for the CIDR notation, again for different subnets or supernets, we will have one broadcast IP and one network IP, which we are typically not assigning to the host. That way, the total number of IPv4 addresses that we have is significantly less compared to the number of network devices that we have right now. So nowadays, you can imagine that all of us have multiple devices which require an IP address. So for example, in our mobile, we require an IP address. In my laptop, I need an IP address whenever I am connecting it to the internet. And more importantly, as we are moving towards the era of smart home, IoT, that area, where all the different devices, they are connected to the internet, they need an IP address. So for example, in my office, I have 2 different machines which are connected to the internet and they need IP address for their interface. I have one laptop which is connected. For that, I need an IP address. My printer is a network printer which is connected with the internet. So for the printer, I need an IP address. Similarly, if I go to my home, I have a smart TV. So the smart TV needs an IP address. I have an Amazon Echo. The Amazon Echo needs an IP address. I have a smart AC that needs an IP address. So that way, this IP addresses, the number of IP addresses that we need, it is not limited to the number of users. Nowadays, a single user might need more than one IP address. So everyone needs some 10 to 12 different IP addresses. And whenever we are moving towards industry automation, where I have multiple different tiny sensors which are connected to the internet, they need separate IP addresses. And people are having wearable devices like smartwatch. So that way, every independent individual devices which are connected to the internet, for that you need an IP address. And you can just imagine that in today's era, we do not need to think of that, well, every person will have a single IP address. Rather, we need to think of that every device that we see around us, that need an IP address. Okay. So that was a kind of massive shift from the idea that ARPANET engineers were envisioned once upon a time. So when the ARPANET was first formed, people thought of that, well, the internet will comprise of the user, that every user is going to connect to the internet. So for every human being, I can just think of one IP address. So that way, they have just thought of that, well, we have approximately 10 billion people in the internet. So I need that many number of IP addresses. But whenever we are moving towards IP addresses per device, the number is enormous. Well, and interestingly, people understood this problem in early 1990s. Well, so at that time, IPv6 was introduced. So this IPv6 has a large IP address space, 128-bit IP address space. So you can have many more number of IP addresses with IPv6. But here is an interesting fact or interesting problem about internet. That any new protocol that you are designing, that new protocol needs to have a kind of backward compatibility, because in internet, say, thinking about an operating system, the operating system works like a standalone software. In your machine, you can just install a patch to update your machine and your machine will start working. But whenever you are thinking of a network protocol stack, in network protocol stack, it is not only about your machine, rather it is the collection of all the devices which are connected to the internet. So if you just design a new protocol and patch your protocol stack, the protocol stack within your machine, that is not going to work. You need to patch almost all the machines in the internet or a kind of large subset of it to make it work. Well, and that was the problem with this IPv6. So people developed IPv6, they envisioned that, well, IPv6 gradually will replace IPv4, where we will have much more larger scale of IP addresses, and IPv6 actually solves many of the problems which were there with the IPv4. But the problem with IPv6 is that the fundamental address structure or the fundamental packet structure in the internet, that got changed. Well, now if you change the packet header, if you just send the packet header from my machine, say for example IPv6 packet header whose size is different, whose address space is different, and I am sending that to a remote host or to a machine, and that machine doesn't understand IPv6. Well, so your protocol is not going to work, and that is the kind of major challenge in deploying any kind of protocols over the internet, that you need compatibility among the devices. It is not like that you independently push your protocol in the internet and it will start working. Well, so and in overnight, you cannot make changes in all the machines, all the servers to support it. Well, so that way, as such, when IPv6 was designed, again the ARPANET engineers, so this internet, the evaluation of the internet was actually based on the experience of its engineers. So as we design new architecture, as we design new protocols, people thought of that, well, I have a new set of protocols, theoretically it should provide good performance. Now, whenever they are going to implement it in practice, they could have found out different kind of issues and they gradually solve those issues to make the protocol deployable over the internet. Well, so one of the very interesting example that you have already learned about the TCP congestion control algorithm that was proposed by Jacobson. And the major challenge of Jacobson was that to make the TCP congestion control compatible with the existing implementation of the TCP. And that way, the excellent engineering piece of work that Jacobson designed was a congestion control algorithm which is completely tuned by the sender. So the in TCP congestion control algorithm, the interesting fact is that the receiver has no role to play in the congestion control as such, right? So in most of the congestion control algorithm, apart from few of its variants like SAP, all other congestion control algorithm, it is completely sender driven. So that way, if I just upgrade the congestion control algorithm under TCP algorithm in my machine, that is going to work because I am going to send the data. So whenever I am going to send the data, I will apply the algorithm and it is going to work. So that was the nice engineering piece or a kind of mastermind, what I would say, by Jacobson, who developed that congestion control algorithm for TCP. But in the innovation of IP layer, we are not that much of lucky. So that way, the IPv6 address that was introduced, although it solves many of the problems, but the fundamental architecture was different. As you can imagine, that whenever I am increasing the address space from 32-bit address space to 128-bit address space, obviously my packet header is going to change. And if my packet header is going to change, it is not the sender who is getting impacted, rather the receiver will also get an impact of it. Well, so that way I will need compatibility with the existing internet, and we have never been able to do so. So that way, even today, we have not been able to, in the last 30 years of IPv6 innovation, we have not been able to deploy IPv6 properly over the internet. We are still going on with IPv4 by doing some kind of jugaad on top of IPv4. Well, so this NAT is one of those type of jugaad. Well, so to solve this problem of IPv6, the remedy that has been accepted widely is to reuse this private IPv4 addresses. So when the IP address space was designed during that time, the designer thought of that it is not always required to connect to your machine to the global internet. Okay. So many of the times it might happen that I will create a small network in a lab scale and we will do an experiment with the protocols. Okay. Now for small network, what set of IP addresses we are going to provide them? So for that, basically these private IPv4 addresses were designed, and the idea of these private IPv4 addresses was that if you want to create a small subnet which is not connected to the internet, then you use this group of IP addresses there and let that machines talk to each other. Well, so that way from every class of IP addresses, class A, class B, class C, a block of IP addresses have been taken. And whenever you are creating a private network, you use that block of IP addresses. Well, so in class A, this 10.0.0.0/8, this block of IP addresses was designated as a private IPv4 address space. Similarly, from class B, it was 172.16.0.0/16 to 171.31.0.0/16. So that block of IP addresses, this should not be 171.31. This is 172.31. So this block of IP addresses were designated as private IPv4 addresses in class B. Similarly, in class C, 192.168.0.0/24 to 192.168.255.0/24, this block of IP addresses was designated as the private IPv4 addresses. Now, the idea of this private IPv4 addresses is that, as I was mentioning, that these private IPv4 addresses are meant for the private network. Well, so the example that I had given, like you develop a small network which does not have any connectivity of the global internet, then for that particular subnet, you can use the private network. Well, now, interestingly, as there is no connectivity with the global internet, this block of IPv4 addresses are reusable. That means you have one subnet here, you have another subnet here. So these two subnets are connected to the global internet. They are only is a set of machines which are talking to each other. So that way, whatever block of IP addresses you are assigning in one group, the same block of IP addresses you can assign to other group. Because there is no connectivity among them and they are going to work independently. Well, so you only need unique IP addresses when you want to transfer the packet in the global internet such that in the global internet, every machine can reach each other. If you are going to use duplicate IP address, there is going to be an IP address one. But if you have two subnets, that subnets are set of machines and they are not connected to the global internet and they are not even connected to each other. So I have 10 machines here and 10 machines here, and this independently 10 machines are creating a subnet without not being connected to the global internet. Then whatever block of IP addresses you are using here, say you are taking 192.168.252.0, that block of IP addresses, to the same block of IP addresses, you can reuse. Okay. So that way, one of the advantage of private IPv4 addresses is that the addresses are reusable. Okay. Now, whenever you are connecting a machine to a global internet, then that network interface must have a public IPv4 addresses to communicate with the global internet, right? And the reason for that is to enable the routing of data packets towards the proper destination. So you cannot have an IP address conflict whenever you are talking about the global internet. But at a local scale, you can do that. That luxury you have at a local scale. So the question comes that how can we use these private IPv4 addresses which were designed to provide IP addresses to the subnets which are working in silos and not connected to the global internet, and how we can use that concept of private IPv4 addresses to solve the problem of IPv4 address clustering. So the idea is something like this, that you create pockets of subnets with reusable private IPv4 addresses. Well, so for example, use the private IPv4 addresses within an organization. So for example, I have the IIT Kharagpur network. Within IIT Kharagpur network, let us use a private address block. So let us use 172.16.0.0/16. Similarly, say in the IIT Delhi network, we use the same block of IP addresses 172.16.0.0/16. Similarly, in the IISc network, use the same block of IP addresses 172.16.0.0/16. That means within an organization, the set of machines that we have, we are just thinking of that every organizations are going to work in silos. They are working isolatedly. That means I am assuming that a machine within IIT Kharagpur network is not going to talk with a machine within the IISc network. So for example, a machine which is in my lab, which is in the lab of our software lab, that is not going to send any data packets to a machine which is in a lab at the CSA department of IISc. Similarly, the machine which is in a software lab of the CSA department of the IIT Delhi, that is not going to send a packet to a machine which is in the software lab of our department. Okay, so you can just imagine that doesn't happen, right? So from your machine, you do not from the machines which are there in our software lab. From there, we do not directly connect the machine which is there in the software lab of the CSE department of IIT Delhi. Right? That we never do. That way, these networks are actually working in silos. Well, so you can just imagine it in that way and think of that. Well, for this set of machines, I will provide the block of IP addresses from this private IP address. Well, and I can reuse the private IP addresses for that block of IP addresses. Now, the interesting observation here is that, based on which this entire idea works, is that not all the users in an organization are active simultaneously. You can just think of that in the IIT Kharagpur network, how many users we have. Possibly something in the scale of 10,000 to 50,000. Right? Now, all of the machines are not going to connect it to the internet all the time, right? You can just imagine the machines which are here in our lab. Well, how many machines are going to get connected at the internet at an instance of time? Well, around 10% of them or 20% of them. Only at the lab hours, every one of you are going to send the data. But again, whenever there is a lab hour in the CSE department, the lab hour may not be same at the EC or the EE department. Well, so that means all these machines are not going to transfer data simultaneously to the internet. Only a subset of them are going to be active at an instance of time. Now, the question comes that, well, whenever these machines are connected to the internet, means whenever I am going to connect IIT Kharagpur network to the internet, IISc network to the internet, and IIT Delhi network to the internet, you remember that for internet communication, I need public IP addresses. Well, for the internal communication within the lab, I can work with this private IP address. But whenever I am going to send the packet from a machine in the software lab, say from the Annex Building software lab, to the outside internet. So for example, I'm going to do a Google Access or I'm going to watch a video over YouTube. Well, So during that time, I need a public IP address, otherwise I cannot send data. And the core idea here is like this, that you map the private IP address of the active users to corresponding public IP address. So that means I have 10,000 machines which are there in the IIT Kharagpur network, and out of that I just observe only 1,000 of them are active at a time. So the machines which are currently active, we just assign a public IP address to them. Well, and the rest of the machines which are not sending data to the public internet or the global internet, they just work with the private IP addresses. Okay. So here is an example. So for example, from IIT Kharagpur network, I have a machine which has a private IP address of 172.16.10.2, and same IP address I can also reuse others. So similarly, I can have another machine which is in the IRC network having the same private IP address 172.16.10.2, and then whenever they are going to send the data to the internet, they have been provided a public IP address. So whenever this machine of 172.16.10.2 is sending data to the outside internet, at that time, I am providing a public IP of 202.141.81.6 to that machine. Right? So that is the kind of core idea. That means whenever, by default, you provide the private IP address to a machine, and whenever that machine is going to send data to the internet, during that time, you use the public IP address assigned to the packets or the traffic flows which are originated from that particular machine. Right? So the question comes that how I am going to do this conversion? Right? How I am going to do the conversion from this private IP to the public IP? So this conversion is being done with the help of this network address translation or the NAT. Right? So NAT is basically an internet middle box that translates the private IP addresses to the public IP addresses and vice versa. And this is how NAT works. That same IIT Kharagpur network, I will have a gateway, and in that gateway, I will have a NAT server which is running. Now, I am having a machine which is being assigned a private IP address, say 172.16.10.2, and whenever I am sending a packet, say the packet is destined from the YouTube server, and this packet reaches to the gateway, well, then and the NAT server is connected to the gateway, and what the NAT server basically does, the NAT server typically maintains a table. So whenever a packet reaches to the NAT server, saying that the source IP is 172.16.10.2, which is a private IP address, and the NAT server sees that, well, this packet now needs to go to the outside internet, so it needs a public IP address. So the NAT server maintains this NAT table where it makes the conversion from the private IP to the public IP. So one of the available public IPs which have been provided to the IIT Kharagpur network. So whenever the IIT Kharagpur network is subscribing the network with the SARNet or National Knowledge Network, so you have seen from the page possibly that IIT Kharagpur network is connected to the NTN Edge network. So whenever the IIT Kharagpur network is subscribing to the NTN Edge network, it can mention that, well, I need some 100 different public IP addresses. So in that case, the NTN administrator will provide that block of IP addresses to the IIT Kharagpur CIC administrator. And the public IP addresses which are used for this NAT conversion are from that block of IP addresses. Well, so whenever the packet reaches to the gateway, the NAT server basically makes this conversion. It provides a public IP of 202.141.81.6. Say for example, with the private IP corresponds to 172.16.10.2, and this mapping is maintained within the NAT table. And now, whenever the packet is going outside the internet, during that time, the source IP, which was earlier as 172.16.10.2, a private IP, that is being replaced as 202.141.81.6, which is the corresponding public IP provided by the NAT server. So that means the NAT server makes a modification in the IP header. So what the NAT server does, the NAT server basically changes the IP header. It modifies the public IP, a private IP to a public IP, and send it to the outside network. Right? And these modifications are typically done in two different ways. One mode is called a kind of tunnel mode. In case of tunnel mode, it actually makes changes in the original IP header. And in another mode, what it does that it adds up a pseudo header on top of the original IP header, and that particular IP header, the additional that IP header that you are adding up, that contains the public IP address and the source IP address. Now, whenever you are providing a public IP address and the source IP address, the packet gets traversed and it reaches to your destination. And whenever you are getting back a reply, say for example, you have connected to the YouTube server, whenever you are getting back a reply from the YouTube server, then what the YouTube server will do, that the YouTube server will look into the source IP field of the incoming packet and use that field as the destination IP. Well, so that particular source IP, the public IP which has been assigned, now the destination IP field of this machine will be replaced by that particular IP, which is the 202.141.81.6, and that will be sent up. Well, and this block of IP addresses from the routing policies from based on that BGP routing or all the different routing algorithm that we have learned earlier, it finds out that this block of IP address belongs to the IIT Kharagpur network. So the packet is being forwarded to the IIT Kharagpur gateway. Now, once the packet comes back to the IIT Kharagpur gateway, then again the gateway consults with the NAT table and finds out that, well, this public IP 202.141.81.6 corresponds to the private IP 172.16.10.2. So whenever the packet is going inside the network, you again change the destination IP as 172.16.10.2 and then apply the corresponding intra-domain routing which is configured for the IIT Kharagpur network. Say it is RIP, routing information protocol. So you use the RIP to send the packet to the corresponding destination which has the IP address of 172.16.10.2. Okay. So this is the typical way the things work. So in the same way, whenever another machine sends back the packet, the source IP gets modified to the destination IP and the new entry is added to the NAT table. And then whenever the reply comes back, then again it does the modification and make these changes. Okay. Now, one interesting fact here is that well, you can argue that I have multiple different machines which can be active, right? So at the peak hours, although I'm assuming that generally I will have some 1,000 machines which will be active, that means, say for example, when the software lab is going on at the CSC department, may not be at the same time a lab is going on in the SC department, but it is highly possible that at peak hours, both the labs are operating and you need a more number of IP addresses. Now, to do that, to support this at a larger scale, what we typically do, we take the help of this end-to-end flow. Now, in the network protocol stack, we have seen that the communications are from one process to another process, or one application process to another application process, and this application process creates a socket. And the individual application processes are identified by IP address and port number. Now, along with every IP address, I can have multiple different port numbers, right? I can have, so the port number is, I have around 35,000 different port numbers which are possible. Now, if I just remove the reserved ports, still I have multiple number of open ports which are available. So we take a combination of IP address and port numbers to scale up such a system. So that means whenever you are forwarding a packet from inside the network, apart from the IP address, you use the port number and you do the mapping with another IP address and port number. Now here you see this particular example, whenever you are transferring the packet, and in this NAT table, I have used two different private IPs. That means the packets are originated from two different flows and two different machines, but they have been assigned the same public IP, but with different port number. Well, so that means this differentiation between the flows are happened between the IP address and the port number combination. And in this particular example, what particularly we are going to do is that rather than uniquely identifying every independent machine in a network, the NAT is maintaining or making a mapping for every independent flow of the network. Well, now from a single machine, even if it is getting connected to the internet, obviously it will not have that 65,000 number of different flows, right? It will have maximum 100 different flows or 200 different flows, even if we think of at a larger scale. Well, so that many number of flows are there, and that many number of flows. If I do a corresponding mapping at the public IP space, I will have more number of port numbers which will be available, and I can use that port number to assign the flows or address port combination to the flows which belong to a different machine. Okay, so that way, by doing this address port combination in a typical NAT, we extend the scalability of the system along. Well, so that is the typical idea of NAT which are being used here, and almost for all the kind of organizational network nowadays, people use private IP address within the network, and they use this concept of IP port combination and the NAT at their gateway to make a mapping from the private IP address to the public IP address. Well, so this is common for almost all the organizations in the world. Well, so they operate in this particular way. Now, this way the NAT provides a kind of jugaad, a kind of takeaway solution for handling the IP address scarcity problem. You see that by utilizing these private IP addresses along with this combination with the port number, we can get a large number of combinations, and for that large number of combination, we can work independently. Right. But the problems which are associated with the NAT are as follows. I guess whenever you are in within IIT Kharagpur, you have faced similar type of problems, or you have observed similar type of problems, that many of the internet protocols and services such as H.2.323, RCell, IRC, PPTP, ICMP, etc., they do not work over such internet middle boxes. Okay, particularly when the outside machines need to initiate a connection. So, for example, I think you have seen that if you do a ping or trace route from a machine within IIT Kharagpur network, which has a private IP address, and you want to do a ping to, say, Google, to some machine which is outside IIT Kharagpur network, that ping doesn't work. Ping or trace route, that doesn't work. Well, so that is one of the problem with NAT, that it doesn't support ICMP directly. And the problem is, again, particular when the outside internet needs to create a connection. So, for example, you have seen that if you just simply run a web server in your machine, although from within IIT Kharagpur network you are able to access it, but from outside IIT Kharagpur network you will not be able to access it. Why? Because whenever you are doing this kind of mapping, the mapping happens whenever the machine inside the network initiates the connection and the first packet reaches to the NAT. Well, at that time it does the mapping. But if the outside machine just sends a packet, during that time this kind of mapping is not there. So you will not be able to forward the packet any further. Well, so this is the kind of challenges that we have whenever we are going to use this kind of NAT. Now, sometimes NAT is combined with DNS to provide such kind of support that, well, the DNS will do a name resolution and find out that what is the corresponding mapping. DNS provides the IP address of the NAT server, which helps in address translation. But that particular solution has a lot of overhead, and that's why in practice we seldom use that. Well, and another challenge with the NAT is that the processing of the NAT tables need to be very fast. Well, many of the times this NAT becomes a kind of performance bottleneck in the internet, because you can see that all the packets from IIT Kharagpur which is going outside at the NAT, you need to do an address translation for that. Well, so that way the NAT server need to work in a speed of a typical router, high-speed router, and that way if your NAT server becomes slow, your overall internet performance within that organization is going to get affected. So these are the kind of challenges or the overheads which are associated with NAT. But because NAT provides an interesting solution for handling the IP address scarcity problem, and it is really a problem nowadays. Means we cannot use public IP addresses in all the machines that we have. We already have more number of machines connected to the internet than the number of public IP addresses that we have. So we have to use some kind of remedy, and NAT provides a kind of nice remedy for that. Okay, so this is all about our discussion of NAT. Now, in the context of NAT, I would just like to mention one particular tool called IP masquerading. So, this IP masquerading is a process where one computer acts as an IP gateway for a network, and all other computers forward IP packets to that gateway. Then the gateway replaces the source IP address with another IP address, typically its own IP address, and forward the packet to the outside network. So this IP masquerader, that is mostly used to hide the IP address of an internal computer of a network. Well, so that means you send the packets to a kind of common gateway, and the gateway replaces the source IP with its own IP. That way, to the outside internet, outside of that gateway, it is something like that. The gateway is sending the packet. So you are hiding the machines which are behind that particular gateway. Now, NAT typically works like an IP masquerader, and the idea of NAT actually evolved from the idea of IP masquerader. So I would suggest or encourage all of you to check this IP mask Linux tool to set up IP masquerading over Linux. Okay, so you can do IP masquerading using IP mask tool, and you can actually change the IP addresses which are being forwarded from your machine. So that is all about our discussion about NAT. Let me know if you have any questions or query, any doubt, any comment up to this point.
Sir, even the currently active internet users will be growing largely, right?
Yes, yes.
So anyway, we'll run out of IPv4 addresses.
Yeah, so that's why. So what people are envisioning that, well, if you make a combination of IP address and the port, so the last idea that I have just mentioned, that for every private IP, we are not going to assign one public IP. Rather, we are going to make a combination of the IP address and the port number. That way, you have 65,000 port number possibles. Now, for every public IP, you can actually support 65,000 different private IP addresses, or at least 65,000 different flows, which are being originated from the machines inside the network. Right? Now, by doing this combination of the IP address and the port number, till now we are able to solve this problem. So till now we are able to do away with the problem of IPv4. Right? But again, you are right that if we are going to the domain of IoT network, where in a single smart home, I can have 1,000 different IoT devices or the sensing devices which are connected to the internet and going to send data. Even this IP address port combination is not going to work. Right? So for that purpose, what typically people uses, and that kind of scenarios actually happen for environment like the smart manufacturing. See, in a company where, or in a manufacturing, or in a process automation lab, where you have such millions of sensors which are monitoring the farm, here actually how you are going to do this kind of things. Here what people does, they make a kind of similar concept of NAT, but rather than mapping from a IPv4 private IP to IPv4 public IP, it makes a mapping from IPv6 address to IPv4 public IP. Okay, so that means the internal network you maintain with the IPv6 network. Well, but whenever you are sending the packet outside, then you make a mapping to a corresponding IPv4 network with a port number. Well, so that is a kind of NAT which convert from a IPv6 port number combination to IPv4 port number combination. So that way it basically works, or it tries to work.
But if it'll convert again back to IPv4, then number of public IPs or IP port combination will remain same.
That is getting reduced. But yeah, the main assumption is that you are not going to run all the machines simultaneously. If you are going to run that, you don't have any solution which are available with IPv4.
Yes, sir. But I mean, what was the point of that IPv6 using and then mapping it to IPv4 again?
No, it is something like that. Whenever you have large number of machines which are even beyond the scope of IPv4 public address pool. So the IPv4 public addresses, you see that, sorry, IPv4 private addresses, they are also limited. Like, so we have that 10 series from class A, 172 series from class B, and 192.168 series from class C. Right? So even if you have more number of devices standard for that kind of combinations.
Okay, so one more thing, sir. You said that deploying IPv6 is hard because each destination PC may not have the same thing.
Right,
For
the destination might not use the IPv6.
Yeah, destination may not use it. So instead of that, if each NAT will use it, then will it not be sufficient to convert each internal IPv4 to public IPv6? And again, at the destination NAT.
Right. One important point is that it is not only about the destination, but about all the routers that are there in the intermediate network. Right? Because the routers need to forward it based on this IP table lookup. Right? Now, the intermediate routers, if they do not support IPv6, then you will not be able to forward the IPv6 packet. So typically people try to work with different kind of remedies. So nowadays, if you look into the machines that we are having, all those machines support dual protocol stack. That means you have an IPv4 stack and at the same time you have an IPv6 stack. Well, so you provide an IPv4 address and there is a kind of standard conversion mechanisms which are being applied. Using that, you make a conversion to IPv6. Well. Now, whenever the packet is going to the outside network, if it supports IPv6 routing, it uses IPv6 routing, otherwise it uses IPv4 routing. But for that kind of keys, you need to do a lot of conversion. So, a lot of back calculation and maintaining consistency across the networks become a challenge because you need to ensure that the behavior of the IPv4 routing for a particular router would be similar to the behavior of the IPv6 routing. Okay. And that way, you cannot just randomly assign some of the IPv6 address to the machines. Right? So in that way, people are gradually trying to. So what people have assumed that, well, if I start applying dual protocol stack, then I will be able to gradually able to move to the IPv6. And that way, some countries internally have started using IPv6. For example, Japan. Or South Korea, so they internally started using IPv6. So it was something like that. Whenever a packet is routed to some machine in Japan, so the gateway to which you are entering towards the network of Japan, that makes the conversion from IPv4 to IPv6. And within Japan, they are using IPv6. Well, so all the routers within Japan have been replaced with IPv6. So that means some countries, or indeed some small countries where you have possibilities for doing such kind of replacement, you can take initiative by the government to replace all the intermediate routers, or even if all the network service providers which are there in a specific country, they come to an agreement that, well, we are going to replace all the machines, all the routers with IPv6 supported routers, then we can do it. But globally, we are not been able to do so. Particularly because although many of the developed countries or the first world countries already have IPv6 supported routers, they have been able to replace the routers. But for countries like even India is a much better scale because the telecom industry in India is one of the kind of richest telecom industry in the world. So that way I know that many of the network service providers in India, they have IPv6 supported routers. But say the African countries, they are not been able to do so. So that way even today the global internet has not have support for completely moving to IPv6. So Pankaj, does it clarify your doubt or anything else?
Yes, sir. Thank you, sir.
So any other doubt?
Sir, suppose in the destination machine, we have some kind of IP-based rate limiting. Then if someone within a network that is access to a NAT, 100 people try to access that site, then that rate limit will be imposed on the public IP itself, right? So then everyone will be penalized.
Can you please repeat once?
So is it clear now, sir? I am saying that in if a destination, suppose there is some site which say in IIT Kharagpur we are inside a NAT. So let's say 100 people are trying to access a site which has a IP-based rate limiting of say one request per second. So say every one of the user is doing one request per second, but since 100 of the users are sharing that connection, sharing the same public IP, won't the rate limit be imposed on the public IP itself? So how do I control this
So
situation?
first of all, typically for the web servers, we do not keep it behind the NAT. So for example, IIT Kharagpur web server and IIT Kharagpur mail server, it is outside NAT and it is always given a public IP address. That is particularly because the outside internet is accessing that. And so this problem of rate limiting will come here because you see that if the NAT is, as I was mentioning, that if the NAT is getting overloaded, then the NAT will become the performance bottleneck. So if you want to make people access to that website via NAT, then again the NAT is going to get a kind of performance bottleneck because as you have mentioned that 100 people are going to access the website via that NAT. So that is one of the reasons, and the second reason is that we do not, for such kind of public servers of an organization where we know that people from the globe or people outside is always going to access that, we do not use NAT there. We keep those servers in front of NAT, and one public IP address is always given there. From the rate limiting perspective, if you are doing a rate limiting on a particular IP address, and if that IP address is one of the NATed IP address, that means a public IP address which is used in the NAT, then obviously all the users are going to get suffered because if you provide some one request per second for a particular public IP address which is assigned to a NAT, then you cannot send more requests than that. So if there are 100 machines which are connected via NAT and they use that particular public IP address, they are going to suffer. But that kind of configurations are not very common in the internet. So as I have mentioned that this rate limiting, all these things are typically being done for web servers and they are typically put behind the NAT. They are not, sorry, they are typically put in front of NAT. They are not put behind NAT.
Okay, sir.
Okay. Anything else? Any other doubt or query?
Yes, sir.
Yes.
Sir, I wanted to ask, like, what is port forwarding and how is it different from NAT IP masking?
Port forwarding is a kind of similar concept, but the idea of this port forwarding is something like that. Okay. So let me do one thing. So I'm taking up this question, okay, because I can try to draw. Not sure. Might have a pen and paper. So if I had access to a blackboard, that might have. So I'll try to prepare a slide on that and share it in the next class. So in broad, what port forwarding basically does, port forwarding typically means, say for example, you have two different machines. For one particular machine, you have well, and for another machine, you do not So I typically run a lab, research lab within our department. It's called a system research lab. So in system research lab, I have one public IP address. Well, so that is actually being assigned by the CNC. Now that public IP address is assigned to one particular machine. Now, what happens that say for example, I design a server and I run a web server which is behind that. Okay, that machine the web server is actually done. One thing is that what I'm going to do is I want the outsiders should be able to connect to this particular particular web server. So how will I do that? Now to do that, what I typically do that this web server is running on a particular port. Say it is running in 8080 port on a particular IP address, and I have another public IP address. Say that public IP address is 202.141.81.2. Well, and the web server is actually running in a machine, say which has an IP address of 10.1.1.1. Well, now what I do that I take the domain name, well, and after taking that domain name, what I do that I assign that domain name with the IP address 202.141.81.2, which is the public IP address that I have, and the fixed port. Typically in the NAT, what happens that it dynamically assign the IP address port combination, but here I do not take the dynamic port, rather I define a fixed port, that I define the port as say 3122. Well, so the DNS resolution, when it will happen, it will say that well the web server is running at a machine 202.141.81.2 at a port 312. Well, and I put a port forwarding rule in that particular machine 202.141.81.2 saying that if any request comes to the port 3122, then you forward that request to the machine 10.1.1.1 and port 8082. Okay, so this is basically called a port forwarding. So the difference of port forwarding from NAT is that in case of NAT, these port addresses which are being provided along with the public IP address, it is decided dynamically. It is decided by the NAT server. Okay, so the NAT server, whenever a connection is being initiated, the NAT server finds out what is an open public IP with a port combination and it assigns them. But in case of port forwarding, I am fixing up the port there. I am saying that the 3122 port, if any packet is coming for that port address 3122, then you always forward it to the IP address 10.1.1.1 at port 8080. Okay, so that way actually we are solving that particular problem. So I think I mentioned here that this problem that initiating the connection from outside network will take a help of DNS. So we take a help of DNS with this kind of port forwarding mechanism. So the DNS says that well, if your domain name is say sondipc.iitkgp.ac.in, then you send the packet to the machine 202.141.91.81.2 at the port 3122. And once the packet comes to that particular port 3122 at the machine 202.141.81.2, I put a port forwarding rule there that any packets coming to that 3122 port will forward it to this private machine with IP 10.1.1.1, where the server is running at port 8080. So this is basically called a port forwarding. So am I being able to explain you? And the application is something like this, that you want to run a web server in a private machine and want the outsiders people to connect to that particular machine for forwarding the data. So is it clear to you? Yes.
Okay, sir. And sir, is it safe to like do this port? Yes, sir. Yes. But sir, is it safe to do this port forwarding?
Yes,
Because
yes,
it
yes.
exposes our machine to the global internet.
Right, right. So So it actually helps that machines which are behind the NAT, but typically if a machine is behind the NAT, the connections need to be initiated by that particular machine. So here port forwarding is helping you to access a machine behind the NAT through a fixed port of one particular IP address. Okay, so the difference from the NAT is that in case of NAT, the public IP and the port is assigned dynamically, but in case of this port forwarding, the public IP and the port that need to be fixed. Okay. If it is dynamic, how people will get to know? So you remember that if you want to connect to www.google.com or www.itkgp.ac.in, the itkgp.ac.in should run in a fixed IP address. If it keeps on changing at every 15 minutes, you cannot connect. Well, because you need to put up that mapping in the DNS. Well, so that way you need a fixed IP and a fixed port. So in case of port forwarding, you can just imagine it's a kind of sub-function of NAT where NAT assigns the public IP and the port dynamically. But in case of port forwarding, we are just doing the reverse thing, that we are using a fixed public IP and the port, but using that fixed public IP and the port which is being mapped to the DNS to connect to a machine which is at a private network. Okay. Any other doubt? Okay, so let us take a break for 5 minutes. So it is 9:05 in my clock. So we'll be back at 9:10, and then we'll start with